Okay, good afternoon. Get started. So end of last lecture, I talked about this Botox and stroke recovery example. And I told you sort of the setup of the problem and the end of the problem, but I didn't really do it. So I wanted to go back and do this. Partly just as another example of a hypothesis test, and then I'll do another example of a hypothesis test, sort of straight from the main part of chapter 26, and then the end of chapter 26 deals with a different kind of hypothesis test. So I'll do that today also. So I'll get through everything in chapter 26, and I think I'll have time to kind of start talking about what happens in chapter 27 that's different, but I don't think I'll have time to really do much in chapter 27 today. So your last homework's due next Monday. I haven't posted it yet. I've been trying to decide how far I want to go. I think what I'm going to do is just go kind of, I'll do a problem or two from chapter 29. So we're skipping chapter 28. I think on Thursday I'll have time to do the main part of chapter 27, enough to do whatever homework problems I assign, and just talk a little bit about chapter 29, enough to do maybe a problem or two from chapter 29 for next Monday's homework, and then that'll be it. And then next Tuesday's lecture, I want to kind of fill in some technical details from chapter 27 that you don't really need to know to do your homework, but I do want you to know for the final exam. So I'll do that next Tuesday and kind of finish up loose ends and probably start reviewing. And then a week from Thursday, the last kind of official lecture, I'll kind of just review and do some examples. And then the Tuesday after that, 2 weeks from today, is part of the RRR week. I have this room reserved, so we can do stuff in here. And so I'll kind of treat this a little bit how I treated the last lecture before the midterm. I'll be here, and you can ask me questions, and I won't really prepare anything per se to do. Okay, so that'll be the Tuesday of the RRR week, which is sort of no new material, nothing like that. And actually, the next week I'll be doing just a little bit of new stuff next Tuesday, but that'll be it. And while I'm talking about it, I guess I'll just mention one other thing, which is that during that RRR week, your sections will also meet. You'll have you won't have anything due, but you can pick up your last homework, your quiz, and your GSI will be there to answer questions. So during that RRR week, the section will kind of meet if you want to, like if you want to pick up your stuff and whatever. Your GSI will be there during your regular section time. Okay, I'll put all that on BSpace too. Okay, so Botox and stroke recovery. So the data I gave you really quickly last time, there are 63 stroke victims. And they are all sort of similar. They report some kind of one or more of pain in hands, loss of ability to wash hands, or loss of ability to get dressed. So when I say loss of ability, it's not necessarily they can't do this thing at all, but they have trouble. Okay. So as a result of their stroke, they're experiencing one or more of these symptoms: pain in their hands, loss of ability to wash hands, or loss of ability to get dressed. And 83% of those, let me say it this way. These 63 all get Botox injections. So these 63 subjects all get Botox injections in their hands. And 83% report significant improvement. And I'm putting the word significant in quotes because this is the usual English usage of the word significant, okay? Just this is on a form, a questionnaire they filled out, and they were just asked to describe, their level of improvement. So one of the possibilities is they report significant improvement or at least some level of significant improvement. Okay, so that's just the regular English usage. As statisticians, we use the word significant in a different way, right? We use it to say that, like if you say a result is statistically significant, that means that the p-value is less than 5%, okay? So in the context of hypothesis tests, significant is a specific statistical jargon kind of word, okay? But that's not the usage I have in mind here. This is the regular English usage of the word significant. Okay, 83% report significant improvement in one or more of these areas. Okay, one or more of their symptoms. Yes. Okay, so I gave you that result last Thursday, and then I kind of said, well, it might be nice to have something to compare this to, because we know that a lot of times people recover from strokes anyway. Like if you just leave them alone, sometimes their brains will sort of take over whatever loss of function they had because of the stroke. Okay, so we'd sort of like to have something to compare that to, and what we have to compare that to is that about 53% of similar patients report similar improvement. And when I say similar, I want to be a little bit, I want to talk about that more, okay, what I mean by similar. I don't mean necessarily that they're identical. I mean, you can't really get an identical, completely the same group of people. So I'll talk a little bit at the end of the discussion of this example about, well, how similar is similar, and is there anything else that could be a possible explanation other than Botox, basically? Okay. So if you think back to the context of Chapter 19 and bias, well, we'd sort of like to make it true that, or actually, let's think back to the very beginning of the book, Chapters 1 and 2. When you conduct an experiment, you'd sort of like there to be no difference between your treatment group and your control group except for the treatment, right? And that might or might not be true here. So let's at the end, I'll talk a little bit about some possible problems with the way they ran this experiment and possible differences between the Botox group and the non-Botox group besides just Botox. Okay? All right. So the question is, can the difference between 83%, the improvement rate for the Botox people, and 53% be explained by chance? Okay? So that's the kind of common phrasing of these hypothesis test questions, is we're basically curious if that difference could just because of sort of randomness, or is that difference so great that it's more than we would expect to see because of chance. So if you think back to my card guessing example, if I got 30 guesses right out of 100, I expect 20, and we sort of thought, investigated this idea of could I sort of have gotten lucky and gotten 20? Sorry, could I have gotten lucky and gotten 30 right, or is that so many right that it's pretty hard to believe that I just did it randomly? Okay, so sort of similar idea here. Okay. So any questions about the setup? Okay. So then if we go ahead and do the hypothesis test, I've laid out these steps last time, and I'll just kind of go through step by step. The null hypothesis says the first part is what I've described as a chance statement, something about chance, which essentially says this, that the difference can be explained by chance. Remember, null means sort of nothing. It means that nothing's going on except for just random variability. Okay, and the B part is something particular to the problem, and this should say something about your box model. In this case, what that says is that it's as if, okay, so when you say difference can be explained by chance, what I mean is that just randomly, this group of 63 people happened to randomly improve at an 83% rate. Okay, so you just sort of got lucky, and you managed to get people that would have recovered anyway, right? A lot of them would have recovered anyway, even if you didn't give them Botox injections. So that's the idea behind the null in this example. And what does that say about the box? Well, it says that really we should have expected to see 53% improvement. And like I say, we got lucky. We randomly observed 83%. Okay, so something like this: should expect 53% improvement. Okay, so this is consistent with saying that Botox has no effect. Null, nothing. Yeah. Do you say that before you actually test it? The hypothesis you can lay out before you look at any data, before you do anything. Is that what you're saying? Yeah, yeah. The alternative is saying that this difference is so great you can't explain by chance. So can't be explained by chance. And it's saying that essentially either Botox works or something else. Okay, so really what the hypothesis test is telling us is it's helping us decide whether or not the results can be explained by chance. If the results can't be explained by chance, the hypothesis test doesn't really tell us why, okay? Just like in my card guessing example, if I guess so many right that you decide that, no, that can't be explained by chance. Like if I got 90 right out of 100 guesses, that can't be explained by chance, but it's unclear why I'm able to do that, okay? It's unclear based on just the statistics, the math, the hypothesis test itself. It's unclear whether or not I'm psychic, or if the cards are marked, or if I'm not really shuffling and I know what order the cards are in, or something like that. You don't have any way of telling why I'm able to do it. Okay, so in the same way here, if we are able to reject the null and conclude that the result can't be explained by chance, it doesn't really tell us why. Okay, so it could be the Botox works, but there might be some other explanation. So once we get to the conclusion, I'll talk a little bit more about other possible explanations. Okay, so then third step is to get the z value. Okay, so this is going to be observed minus expected divided by some standard error. So I need to do some math there. But just sort of think about it on top here. All the calculations should be done assuming the null hypothesis is true. Okay? If you think about what the p-value says, the p-value says what's the chance of getting data like we got or something more extreme, given that the null hypothesis is true. So that's where our expected value comes from. Our expected value comes from the null. And that's what I have reflected here in this B part of the null hypothesis. We should expect 53%. We actually observe 83%. And now we have to get some SE. So in getting that standard error, we want to think about a box model. Okay, we have 63 people. And we have ones and zeros in this box. So the ones represent people that get better. The zeros represent people that don't. What percentage of ones should I put in that box? Or can I put a percentage of ones in that box? Any thoughts? Guesses? Anyone? A couple murmurs. Didn't hear anything clearly. Anyone want to raise a hand? Say? Yeah. 53%. Right. Okay? So we're doing that because of the null hypothesis. The null hypothesis tells us that we should expect 53%. So that's what we're going to, have as our expected value. Okay? Expected value for these draws should be 53%, so that's what should go in our box. Okay? 83% is the sample value, right? The observed value. Okay, so based on this, we have a box model now, so we can get the SD of that box. And SD of that box is going to be 1 minus 0. And part of the reason why I'm emphasizing the box is just to make clear what your standard deviation is going to be, right? This is the standard deviation of the box, so I want to use 0.53, 0.47 to calculate the SD. I don't want to use 0.83, 0.17, right? I don't want to use the sample SD because the null hypothesis actually tells me what the box looks like, okay? So, whenever you look at the formulas in the book, they all involve the standard deviation of the box model. And like I say, when we do a hypothesis test, we're always assuming the null hypothesis is true. So once you assume the null hypothesis is true, you should use it not only for your expected value, but you should use it for your SD, okay? So that comes out to be about 0.5. And SE sum is square root of 63 times 0.5, which is about 6.4%. Oh, sorry, it's about 4. And then SE percent is 4 over 63 times 100%. So SE sum divided by number of draws times 100% is about 6.4%. So finally, Z is equal to 83% minus 53% and divide by 6.4%. And I told you at the very end of last class that comes out to be 4.7. So that's Z. Okay, so it's something you might, just kind of a reminder here, whenever you're doing a Z value, and this is really true whenever you're converting anything into standard units, you want to make sure these things agree, right? In this case, this is an observed percent, this is a expected percent, this is an SE for percent, okay? So make sure they all, agree. Like make sure you don't put a 4 on the bottom. 4 is the SE sum, it's not the SE percent. So just sort of try to get in the habit of checking, because that's a pretty common mistake to use the wrong SE or to use the SD or something, okay? Okay, so that gets me my Z. And now, again, I want to go back to the logic of the p-value. That's our next step. So as a Z value, this is 4.7. And this is off the table, right? 4.7 you won't find on the normal table. It's too big. So this p-value is very, very small. Okay, this is really far. 4.7 standard errors away from what we expected is really far. So the p-value is essentially 0. Okay. And just to say again what the logic of the p-value is, the p-value is the chance of getting data like we got, or more extreme, farther away, given that the null hypothesis is true. So the null hypothesis is telling us that we should expect 53% in the middle, right? So the logic of this process is that we assume at the beginning of our calculations that the null hypothesis is true, and then at the end here, we see that our data basically contradicts that assumption. This is so far away from what we would have expected that it makes us believe that there must be something wrong with our assumption. Because the data really happened, right? The 83% really happened. And if you observe a result that is incredibly unlikely, given your assumption, well, that casts doubt on your assumption, right? It makes you think, well, maybe that 53% isn't right. Maybe the people that take Botox really do have a higher rate of improvement than 53%, okay? Certainly the sample percentage is higher, but we're trying to say something about the general effect of Botox, that it does something, and it gives you a better chance of improving, okay? All right, questions, thoughts on that? Okay, so let's do the conclusion. So the conclusion, I've said, has basically 3 parts. The first part is the statistical jargon thing, okay? So the example I did last time was that we read with the card guessing, getting 30 right, the chance of getting 30 or more right is a little bit less than 1%. My conclusion, first of all, was that I reject the null at the 1% level, meaning that my p-value is less than 1%. Here, I'm off the table. My p-value is essentially 0. There's like almost no chance of getting an observed value of 83% or more if the box really does have 53% ones in it. So that's why I think that's not true. So I reject the null. Okay, if you said reject null at 1% level, I wouldn't say it's wrong. But I'm pretty comfortable just saying I reject the null. I don't really believe the null could be true here. This is so far away that it's sort of unbelievable. It's unreasonable to think that it might be just chance. Yeah, so then B part is that this is not just chance. This is what I call in my original description of the conclusion a chance statement, right? Statistical jargon, chance statement, and then finally something particular to the problem, which in this case I would say that I'll be a little bit vague here. I'll say Botox works or something else. Okay, so I've determined that this can't be explained by chance, but I want to think just a little bit more about whether or not there could be any other explanation besides Botox. Just like in my card guessing example, if I claim to be psychic, you might say, well, wait a minute, maybe the cards are marked, or maybe there's some other explanation besides the one that I'm trying to make. Okay, so through this experiment, I'm trying to decide whether or not Botox works, but I should be a little bit careful and think about what some other possible explanations might be. So in thinking about that, any questions actually before I do that? I'll talk a little bit more about this kind of more conceptual part. But any questions about the math or the structure of the hypothesis test in general? Yeah. The alternative hypothesis you'll never use. I'm not sure what you mean by that.
So we always assume that the null is true.
Yes, you always assume the null is true. You always assume the null is true. Yeah. The alternative is usually somewhat vague. It doesn't tell you anything about any box model. If the alternative is true and Botox works, that doesn't give you any idea of how well it works. You know what I mean? So it doesn't tell you oh, Botox works and they should have a 70% improvement, or they should be a 80% improvement. So because the alternative is just kind of the counter argument to the null, it doesn't give you enough information to do a hypothesis test. You can only do the hypothesis test if you're told basically what your expected value should be at least. What are you comparing it to? Which is what the null tells you. Does that make sense?
So it's a useless hypothesis.
I'm sorry?
Is alternative hypothesis useless?
Is it a useless hypothesis? Well, it's useless in the sense that it doesn't enable you to do any math, right? The null hypothesis enables you to make this assumption, get the expected value, get a z-value, get a p-value, do the math, okay? The alternative is, I think, important. It's not useless because it gives you, it tells you what you should believe or what you should think if you reject the null, right? So there's this tension between these two possible explanations, and we're trying to decide which one of them we believe, right? If we get a result that's very close to the expected value, like if it was 55% improvement or something like that, that would make us think, well, that's not very impressive. That doesn't really give me any reason to use Botox. because it doesn't really help. It doesn't really look like it helps you. If it does help you, it helps you very, very little. Okay, and that's so when you get something really far away like this, then that gives you an argument towards the alternative that okay, well, we're going to reject the null. I don't believe this is due to chance. Botox looks like it's really doing something. Okay, and then sort of in between, it may be a little bit I don't know, a little bit subjective which one you want to believe. We have these rules of like, okay, if p is less than 5%, reject the null at the 5% level. The alternative looks better than the null, basically. Okay, but that's an arbitrary line. There's no reason why we shouldn't use. There's no real reason why we shouldn't use some other arbitrary line, 10%, 1%, whatever. Okay, so because that's a little bit, I don't know, kind of subjective towards the middle, it's arbitrary anyway, then I think it's important to sort of make clear what you're trying to decide between, and then when is one definitely look better, when does the other one definitely look better, and then in the middle, we want to know like, well, when is it a little bit of a gray area? Okay, does that help? Yeah, okay. Any other questions? Okay, so when you look at an experiment like this, I think if you want to kind of look at it critically, what you want to think about now is, well, what are some possible differences between these 63 subjects and this other group of people, this group that had a 53% rate of improvement? I haven't told you a whole lot about these other people, so you might wonder, like, what's the deal? I'm sort of saying, well, they're kind of similar, but how were they chosen? You know, are they sort of, do they have sort of similar kinds of strokes? So you might ask them questions like that. So you can ask if you want, or if you can just see anything that's problematic. Do you see any differences between those two groups that are obvious, other than just the Botox itself? Anyone see any issues, problems, specific questions you might wonder about that other group? Anything? Yeah. How many people? So this is a. So when I read this study, it was unclear how many that was. That was believed to be sort of a background rate of improvement for a large number of people. Okay, so we're assuming that it's at least fairly stable compared to the 63. And one way of thinking about that is that it's not random. That the number of people is large enough that the standard error is going to be very small, if that's sort of what you're thinking about. Yeah? Okay, so he's saying that the group that we're testing, the 63, is probably a lot smaller than the other group. So I'm not sure why that bothers you. I mean, you can compare to, like, you'd sort of want it that way, right? If you want to compare this group of 63 to something else, if you had like data on, you know, sort of all stroke victims or like thousands of stroke victims, it seems like that would be a good comparison to make, right? Because you're comparing to something that's sort of like a really kind of robust, accurate idea of what we should expect. That make sense? So I think that should, you know, be a plus. That's I think a large group of people. Yeah.
Do you know if the similar patients are being treated in any other way, or if they are just being left alone?
Do we know if they're being treated in any other way, or they're just being left alone? We'll presume, I guess, that they're being any additional treatment they're receiving is similar to that of the Botox people. Okay, which may not be entirely true, because it's, like I said, those people are not, they're not recruited into an experiment in exactly the same way as these people. But probably that's fairly similar. Yeah, they're given sort of a similar questionnaire. They have similar kinds of problems with their hands. That part is pretty similar. Did you have a question or comment? Anything else? So let's think about let's think about the polio example that we did a long time ago, right? So what was we had these two polio examples. One of the experiments was sort of not so great, and one of them was done pretty carefully. Do you remember any of the problems with that first example that might also come up here? Yeah. Yeah, there's no placebo, okay? So I'm just going to say differences between the 63 subjects and the others, the other people, where the 53% comes. There's no placebo. Okay, so for the polio example, there also was no placebo. Okay, the kids knew if they were getting the polio injection for the first experiment, so they knew whether or not they were getting an injection of the vaccine. And we kind of talked about that a little bit, and I said that, well, for that example, it probably doesn't make that much difference because it's not like their behavior is going to be very different probably just because they're vaccinated. So risky behavior for getting polio is things like going to a public swimming pool and, like, I don't know, hanging out with a lot of kids, things like that, eating dirt maybe. So these things are things that probably are not going to be very different if you're vaccinated and if you're not vaccinated. Probably your behavior is going to be fairly similar. And I mentioned at the time, if you're testing something like an AIDS vaccine, you want to be really careful because if people think that they're vaccinated for AIDS, they may be more willing to or more, I don't know, more likely to engage in risky behavior, okay? Then there's definitely risky behavior that you might or might not engage in. So that's a problem there, okay? So what about this? If there's no placebo here, so you know whether or not you got an injection of Botox, what do you think? Do you think that's a problem? Or do you think it's maybe not a problem? Any thoughts? Yeah.
Maybe if you know you got it, you want to say that you improved significantly because you don't want to think like wasted on the survey. Even if you have a small improvement, you want to say that it's
Yeah, good. So she said that maybe if you got the injection, you sort of want to tell the researchers that it helped, okay? Maybe you want to feel like that, the time wasn't wasted or that it really did something or whatever. And part of the problem here is that this is incredibly subjective. It couldn't really be any more subjective to ask people like if their pain has gotten better, if they can wash their hands better than they could before, if they can get dressed better than they could before. Very subjective. Something like polio or AIDS or something like that, you pretty much either have it or you don't have it. It's not this kind of subjective measurement you're doing. So because this is so subjective, there can be a strong psychological effect if you've gotten the treatment, if you've gotten an injection in your hand. You might just think, oh yeah, I do feel better. It doesn't hurt me as much as it did before. And especially with these things, you might sort of just get used to it, right? You might, on some level, be experiencing the same level of pain, but you sort of got used to it because it's been going on for a while, right? Or you've kind of gotten used to or figured out how to like wash your hands a little bit better or get dressed a little better through practice. And that, like I said, that's very, very subjective. And so because of that, if there's some psychological placebo effect going on that you sort of want to get better and you want the researchers to feel like they've done something to help you, you might be more likely to say that you've gotten better, okay? So this, I think this is certainly important, okay? What else? Any other thoughts? Or questions or comments? A couple of other things I think are relevant. Another way you might think about it if you want to try to get at some issues is you might think about this the way you would in chapter 19 and think about kind of selection issues, non-response issues, and response issues. So this is sort of a response issue that it's a subjective measure and you're like, you have this difference because of the sort of subjective nature of the question. You might tend to have different responses than, in this group that got Botox compared to the group that didn't. So any thoughts about what we might think of as either selection issues or non-response issues? Yeah. Okay, so at some level, so he said basically, they weren't randomly chosen. So it's unclear, it's certainly unclear from the description exactly how they were chosen. Even if they're chosen at random, well, okay, so let's think about it as a selection issue. So sort of selection. So there's some population of stroke victims that have similar symptoms, and yeah, so if these are not selected at random, then you might wonder how they were selected. Are they people that were selected because their doctors thought they were good candidates to get this treatment? Are they, if that's the case, if the doctors thought for some reason, oh yeah, there's this experiment going on, why don't you go in it? Why don't you be a subject in this experiment? I think you're a good candidate. These may be people that for some maybe somewhat intangible reason, may be people that were more likely to recover, okay? Or less likely, it's hard to tell exactly how that would work. But if this selection is done by some hand picking in any way, then it's a problem, okay? So it's a potential problem anyway, that through the selection process, you may get people that are more or less likely to recover. Okay? So something that happens fairly often when doctors choose who's going to be in the experiment is they tend not to choose people that are extremely severe cases, because there's some concern that giving them at this test procedure, this injection, may put them over the edge and make things really bad. Even if it's a very small negative effect, maybe Botox makes their hands swell up a little bit, or there's some kind of a reaction, and if they're a really severe case, you might be worried about something like that. That's particularly true for things where the treatment is surgery. So if there's some surgery that people are trying to test, it's typically you won't see people that are really, really in bad shape be candidates for an experiment where surgery is the treatment, because they're worried about any complications from the surgery happen, you might kill the person, right? Okay. So for this injection, it's probably not quite so bad, but still, there's probably a little bit of hand picking by the doctors, by the investigators. Okay, so there's one more thing that strikes me about this that might be a problem. Okay, so we sort of talked about this placebo thing as kind of you might think of it as a version of response bias. This has to do with selection bias. Yeah? Non-response bias. So yeah, so people that are willing to be in this experiment, this is essentially for the polio, sort of analogous to the polio example with consent or non-consent. Right? The parents had to consent to get the polio vaccine, and the consenters tend to be wealthier, and they tended to, in that example, be more likely to get polio, right? Here, well, let's think about the consent, non-consent. And I think what she said is right, that the consenters may have more interest in improving. Okay? They may be people that are like, oh, this is so awful, I'm willing to try anything, kind of thing, right? And then when they get the injection, they may be more prone to think that it helps them. It's one issue. And another issue is that if they have more interest in improving, they may be doing other things. So someone brought up this idea that maybe the people that are in the experiment have different other treatments going on compared to the other people. Well, if that's true, then the consenters probably are more likely to do things like be diligent about any physical therapy that may be an option. They may be more likely to if there's any way that like diet or exercise or anything like that can help them, they might be more prone to do that. And they may be just generally in better health besides the stroke. And just being in general health and, besides the stroke might make them more likely to improve. Okay, so there's a variety of reasons why the consenters might be different, okay? And so that's also an issue. Okay, so how could we correct these things? Any thoughts? I mean, we can't with this data. With this data, we're sort of stuck, right? We're sort of stuck at the end with saying, well, Botox works, or maybe there's something else. Maybe one of these other things, or some combination of these things, explains this big difference that we observe. I mean, this might well make a difference of 10% or so, maybe more. It's hard to tell, right? How much these things might make a difference. These are serious differences between the Botox people and the non-Botox people. So, okay. So if you were to do another experiment, what might you do differently? Any thoughts? So what do we do differently in the second polio example? Anyone remember? Yeah, you have sort of a better, well-defined control group. You could call this a control group where the 53% comes from, but it's not a particularly good control group because there are all these differences between the treatment group and the control group besides the treatment, right? So what they did in the polio example was they took all the people that consented, right? All the consenters, and randomly either gave them the polio vaccine or a placebo, okay? So in the selection process, they're taking, well, I guess both of these things are relevant here. We're taking only the people that consent, and it sort of doesn't matter how we select our initial pool of people because our comparison is just going to be within that group, right? So whatever group of stroke victims you start out with, you take the ones that will consent to be in your experiment, divide them randomly into two groups, give half of them Botox and give half of them a placebo, okay? So that sort of deals with these issues that now we have a group that is only consenters, so that's not an issue, and we give the control group a placebo, so that's not an issue. And this part isn't really an issue because we're only comparing people in the same selection group. We're not trying to compare them to some other group, of people that weren't selected by the same process, okay? Okay, so that's how you might do a better experiment, and that was done in this case. There was a better experiment done after this one, and we don't know quite enough to talk about it yet. So to talk about the math in that example, it's an example for chapter 27, so I'll get to it on Thursday, okay? But there is a second part to this story. Okay, questions about this one? Okay, so that's that. I want to do, actually let's take a little break. Since the example is just so long, I'll just take a little break and then I'll do another chapter 26 example. Okay, so let's do another example. So there's a rule or a guideline that I'd like to tell you, but it doesn't really make sense for me to tell you until you understand why there is something that needs a guideline, okay? So I'm going to do like half of an example until this issue comes up, and then I'll tell you what you should do, right, to deal with it, okay? So I'll do this example with like sort of do half of it, and then I'll kind of stop and talk about some stuff, and then I'll come back and finish the example. Okay, so the example is this. So suppose we have, there's 1 year where we look at MSAT scores, and the national average MSAT score is 519. The SD is 110. Okay, so suppose in this year, there's a simple random sample of 100 students who took MSAT, say in California. And for this simple random sample of 100 students, the sample average is 504, and the SD is 100. So the question is, did all California students have a lower average MSAT score? Or can this difference be explained by chance? Be explained by chance. Okay, so sorry, I ran out of room. So can this difference be explained by chance? Okay. So any questions about the setup of the problem before I get started? Okay, so our null says that null, part A, says that this difference can be explained by chance. Okay. So what does the B part say here? What do you think? What does the B part say about the situation? If that difference can be explained by chance, what does that tell us? Yeah. Yeah, good. The average of all California students is 519. Okay? So it's essentially saying that there's nothing special about California. It's not any higher or lower. It has the same average as the whole country. Okay? The alternative says that it's not just chance. That California has a lower average. Okay. So, yeah, question. Yeah, so the question is this the format you should do it on the exam? So I would like you to have all of these elements in anything you write on the, any hypothesis test you give on the exam. So I think probably the easiest thing for you is to do it exactly like this, just to sort of do it outline form. Null hypothesis says these two things, alternative says these two things, and just get in that habit, okay? If you left things out, I would take off points. So if you just said, like if you left out the chance part and just said, null, average of California is 519, alternative, California has a lower average, then I'd take off, a couple points or something, okay? So I don't actually care if you have like A, B, 1, 2, and all that kind of stuff. But I think you might as well get in I think it's a good habit, right? You might as well just do it the way I do it. And then, yeah, you make it pretty, you'll be more sure not to leave anything out, I guess, if you do it that way. Okay? Any other questions? Okay, so let's think about a z-value. So this is going to be observed minus expected divided by a standard error. Our observed is 504. Expected, according to the null hypothesis, is 519. And then I'd like to get the standard error. What kind of standard error is that going to be? Standard error for what? It's for the average, right? This is an average. This is an average. This should be SE for the average. So SE average we get by taking SE sum divided by the number of draws. Okay? And number of draws is going to be 100. SE sum we get by doing what? What's the formula for SE sum? Anyone? I'm sure you know, right? Yeah. Okay, so square root of the number of draws times SD of the box. Okay? So that's why I'm making you actually say it, is that it's the SD of the box that we're interested in. Okay? So why am I emphasizing that you want the SD of the box? Because there are two SDs over there, right? So yeah. So you're suggesting that we should use the 110?
No, the 590. Oh, yeah.
The SD of the nation?
The 110.
Okay, so you're suggesting the 110? Let's vote, just for fun. Who thinks we should use 110 up there? Who thinks we should use 100? So we should use 100. Okay? Now, here's why. What's the box? The box is California. Do you know the SD of California? No. What you know is so you don't actually know the SD of this box, right? So you don't actually know this for sure. But you have these two choices. One of them is the SD of the whole country, and one of them is the SD of a sample taken from California. Okay? So what's going to be better? I mean, they both are sort of, not crazy, right? They're both at least standard deviations for SAT scores. But the problem is, and the problem that statisticians really hate, is that the national SD might be biased. There's no reason to think that the California students in general have the same SD as the whole country. They might be more spread out, they might be less spread out. It's a little bit hard to tell, okay? And at least the SD of the sample is a simple random sample taken from the box, okay? So at least it's an SD of the right kind of people. They're all California students. You have a simple random sample of them. So that's not going to be biased, right? There's no like selection bias or any other kind of bias that's going to go on with that sample. That's using the bootstrap method. It's taking a sample SD and using it as an SD of the box. And I've said to you, this is generally a good thing to do, It's a reasonable thing to do to use the bootstrap method and estimate the SD of the box based on the SD of the sample. It's pretty accurate, okay? So like I say, the problem is that the other SD might be pretty bad. Now, in this problem, you know, California and the whole country might be fairly similar. But what if the group I'm comparing it to, I said, you know, 1 year they give the math SAT to, I don't know, people in I don't know, Guam, okay? And the Guam average is 519, and the SD in Guam is 110. And then we compare the California sample to that. And now, you know, it sort of feels like there's really no reason to think that Guam should have the same spread as the California people, okay? Our null hypothesis tells you the average is going to be 519, so that's set. You know, it's clear that these two numbers are right. But what's going on here shouldn't be like, you know, you shouldn't have to make this decision, well, like, is California the same as the nation? This is kind of a subjective thing, right? What if it's, you know, I don't know, what if I'm comparing it to some group that really is quite different? Then you could be making a pretty big mistake by using the SD of that other group as an estimate of the SD of California, okay? So like I say, you know, in this particular example, it's probably not horrible. The national SD for MSAT scores is probably not wildly different from the SD of the California MSAT scores. But there's nothing that says, there's no like math or statistics reason why those two places should have the same SD. Just like if you take, you know, like I said, like Guam or, I don't know, I don't want to pick on any country, but I don't know, Poland, I don't know, it's sort of, they're Polish jokes, I guess, or something, right? So there might be a group that has really different MSAT scores, okay? And there's no reason to think that they should have the same spread, okay? So, okay. So, questions on that issue? Okay, so let me write it down. And then I'll come back and do the math. This is the part where I take a break from the problem and write some stuff down, and I'll come back to it. Okay, so we want SD of the box. Okay, this is generally true, right? We want the SD of the box. So if we know it, or it is implied by the null hypothesis, use it. Okay? If not, use sample SD to estimate SD of the box. And like I said, this is the bootstrap method. Okay, so let's think about what this means. Okay, so actually I want to write one more thing. If you are confused, think hard about the box, okay? About what the box is, okay? So I think that's a common source of confusion in this problem, is that people think, well, the population is the nation. Well, it's not. The population is the state. It's California. So that's the thing you want to use the SD from. So probably a lot of you that thought we should use the 110 had that in mind. Like, oh, the nation, that's the box. This is like draws from the nation, so we should use that SD, okay? And it's not quite right. The SD is really, or the box is really California. So if you're confused, think hard about what the box is and whether or not you know the SD of that box, okay? So like I say, if you know the SD of the box, or if it's implied by the null hypothesis, go ahead and use it. So why does this issue not come up until now? We've done a couple of hypothesis tests already. Why isn't this coming up until now? Well, in the previous examples, the null hypothesis has always told us what the SD of the box was, sort of indirectly. So that's the case where it's implied by the null hypothesis. So think about that first example I did with the card guessing. So the null hypothesis there told us that essentially I'm just guessing at random. I have a 1 out of 5 chance of guessing correctly. So that tells us the box has a 1 in it and 4 zeros. I can calculate the SD of that box directly. Okay? I don't need to figure out any sample SD or do anything else. The null hypothesis tells me enough information to figure out what the SD of the box is without doing anything else. Okay? In the Botox example, same thing. The null hypothesis told me that there are 53% ones in the box, 47% zeros. I can calculate the SD of that box directly. It's implied by the null hypothesis. All right? What makes this problem different is that the null hypothesis tells us the average of the box, and that doesn't help us decide what the SD of the box is, right? So what we know about this box, what the null hypothesis tells us about this box is that this box has an average of 519. Okay, that's what the null tells us. It doesn't tell us what the SD of the box is, right? The box could have an average of 519, and it could have an SD of 110, or it could be something else. It could be 100, it could be whatever, okay? In those other examples, if the box has 53% ones in it, I know what the SD is. I can calculate it directly from that information, so I don't need to think about doing any kind of bootstrap method, right? What the bootstrap method would tell me in those cases, in that case, is it would tell me that like the sample SD would be using 83%, right? The Botox example had 83% ones in the sample. So using the bootstrap method would be using the 83% to get the SD, estimate the SD of the box. And I didn't do that, right? I didn't do that bootstrap thing because, again, the null hypothesis gave me enough information that I could calculate the SD directly. Okay, so what makes those problems different is really something about the box. In those other two examples I did, both the card guessing example and the Botox example, the boxes just have zeros and ones in them. So since they just have zeros and ones in them, knowing the percentage of ones allows me to calculate the SD of the box immediately. This box is more complicated. This box is California, and each ticket has an MSAT score on it. It's not just ones and zeros. So then, knowing the average is 519 doesn't tell me what the SD is going to be, right? It's more complicated. Okay, so not only is this an issue between whether or not the null hypothesis, well, it's an issue of whether or not the null hypothesis tells me what the SD of the box is, but what makes this very subtle is that it depends on what the box looks like. If you're dealing with a box of zeros and ones, this issue will never come up because the null hypothesis will always tell you what the SD of the box is. Zeros and ones, it doesn't come up. With averages, it does come up because I can tell you what the average of a box is, and it doesn't tell you what the SD of the box is, right? Okay, so that's that difference there. Another case where this comes up, which is a little bit subtle, is if if my null hypothesis says something like, I'm rolling a die, and the null says the die is fair. If I tell you the die is fair, it tells you exactly what the box looks like. Okay? So if the null says the die is fair, even though I might be doing something with averages, a fair die, I can calculate the SD of the box directly. I don't have to worry about the sample SD. Okay, so there's certain examples where, like always with zeros and ones, and sometimes with other things like dice, the null hypothesis will tell you exactly what the SD of the box should be. Okay, but this one doesn't. Okay, questions, thoughts? Okay, so let me do the math. SE sum here is going to be square root of the number of draws is square root of 100. SD of the box, now again, I'm going to use the sample SD, which is 100. This is the bootstrap method. So I'll say this is a bootstrap estimate of the SD of the box. And that is 10 times 100 is 1,000. Okay. And let's get another board. So SE average is SE sum divided by the number of draws, so that's 100. And now Z is going to be 5 0.04 minus 519 divided by 10. So this is negative, I guess I have 15 on top, 10 on the bottom, so negative 1.5. Wait, I did something wrong. Oh, no, I didn't. Yeah, okay. I think that's all right. Okay, so then I accidentally did use different numbers in my example that I wrote than what I had on the paper, so I don't know what this is. I didn't bring a normal table today, which is unusual. So sorry, does anyone have a normal table by any chance? Look that up. Yeah, 1.5 gives you what? About 7%? Okay. So it's like, oh yeah, actually I know this. It's 83.85 in the middle. 86.6, oh, okay, never mind. 86.64. So yeah, so that's about like, I don't know. Yeah, almost 7%, I guess. Well, actually, let me do it this way. It's actually this part, right, that I care about. It's the same chance, same area, but this is the tail that I care about. So it's about 7%, okay? So that's a little bit bigger than that's a p-value that's a little bit bigger than, I'm sorry, I should be a little more clear here. So up to here, that's my z-value. This is my p-value. This is step 4, p-value. Okay? Draw this picture, get that. And then the conclusion, step 5, is that I can't reject the null. This p-value is bigger than 5%, so it looks like it could be just chance, could be just random. So California could have the same average. Okay? So any questions on that? Okay, so the main lesson for this example is this idea of which SD I should use and how to think about that. Okay, so so those examples took longer than I thought. I want to at least get the idea of another kind of hypothesis test out there. I won't have time to do an example, I think, today, but I do want to do the explanation at least. So the hypothesis, this other kind of hypothesis test, this is the last section, section 6 of chapter 26. This last section talks about a different kind of hypothesis test. So as a kind of, I don't know, transition into that example, I just want to ask you, what justifies me drawing the normal curve here? It's an average. So what should I check to make sure that the normal curve makes sense? Any thoughts? Yeah, I might want to check expected value plus or minus 2 SEs, and also check that it's at least 25 draws. So it is at least 25 draws. I have 100 draws for my box. And expected value plus or minus 2 SEs. So expected value, according to the null hypothesis, is 519. Standard error is 10. So if I went 2 standard errors either way from that, it's well within the range of possible MSAT scores, right? Okay, so there's no problem with the normal approximation. What if that fails? Okay, so if that fails, there are still some things that we can do. And the thing detailed in the last section of chapter 26 is what to do if the number of draws is less than 25. Okay? So a one-sample t-test is used when less than 25 draws. And there's some other things that I'll tell you now, and then I'll detail them a little bit later. The second one is that the SD of the box is unknown. So we're going to use the bootstrap method. Okay? And the data is not too different from the normal curve. So I'm going to tell you what to check here, but it won't really make sense until I talk about how to do a t-test, okay? But I just want to lay out here, first of all, when you do it. And the first thing to check for is really this first one. It's when you notice that the number of draws is less than 25, then that won't work, right? The regular z-test won't work because we can't look up the p-value from the normal table if the number of draws is less than 25, okay? So when we have less than 25, that's your first clue. And then this is usually just true, that the SD of the box is unknown. And then this is basically a check, you know, that nothing's too crazy. So check sample average plus or minus 2 SD pluses. Okay, and I'll say what an SD plus is as I go through the how to do a t-test, okay? But that's the check you do. And you know, it looks familiar, right? You're taking the sample value plus or minus 2 somethings. Okay. So let me describe, how this is different than a one-sample z-test. So almost everything's the same. Okay, the null hypothesis, the logic is the same. The alternative logic is the same. When you do a z-value, it's not going to be a z, it's going to be a t in this case. Just call the t-value. The math is actually the same. We'll take an observed value minus expected value, divide by a standard error. The reason why it's called a t instead of a z is that the z-value corresponds to the normal table, and we're not going to use the normal table. Okay? Again, the reason why we're not using the normal table is because the number of draws is so small. Okay? Excuse me. Okay. So this actually will look very similar, the calculation in this part. And the p-value, well, the table, the t table looks a little bit different. So when you look things up to get your p-value, it's a little, you know, using a different table, and I'll describe the differences, but it's kind of conceptually the same, and your conclusion is the same. Okay. So the main differences here show up in steps 3 and 4, the math parts. Okay. So let me just say what those are. Differences between z and t. The first one is that we use SD plus instead of the SD. And the SD plus is just this small little correction. Okay, so the reason why we use this is actually because the SD of the box is unknown, because we're doing the bootstrap method. And there's this kind of technical reason why the bootstrap method tends to underestimate the SD of the box. And you can think about this maybe, if you think about like the stupidest example of all, if you have one point in your sample. If you were to try to estimate the SD of the box based on 1 point, what would happen? Well, the average of the sample is whatever that 1 point is. The deviation from average is 0, so you would sort of think, well, my only estimate I can make of the SD of the box would be 0. The SD of the sample is 0 if you only have 1 point. Okay? So obviously that's not a very good answer, right? The box probably does not have an SD of 0. So when samples are very small, you have this issue that you tend to underestimate the size, that you tend to underestimate the SD. So if you had like 2 points, well, the average is right in between. And so those 2 points are pretty close to that average of your sample, tend to be, okay? So anyway, this is a general idea that if you use the SD of the sample as an estimate of the SD of the box, it does tend to underestimate it. So I've told you before that the bootstrap method works very well. Really, it works very well when the sample size is fairly large, okay? When the sample size is fairly large, number of draws is large, this thing is very close to 1. But when the number of draws is very small, like when you're doing a t-test, it starts being an issue, okay? So if you have like 5 points, then this is making a difference, okay? If you have like 25 or more, which is when, you know, you tend to use a normal table anyway, this is very close to 1, so you can kind of ignore it, okay? It doesn't really matter. I only care if you use this when you're doing a t-test. But like I say, this is actually, the reason why we're doing this is because we're using the bootstrap method. So anytime you use the bootstrap method, it's kind of technically correct to use this little SD plus formula, okay? Use the SD plus exactly like you would use the SD, right? Okay, then the second difference is that there's this calculation, which is sort of the simplest formula there is, degrees of freedom, which is sometimes abbreviated just df, is the number of draws minus 1. Okay, so I'll say a little bit maybe on Thursday about why that is relevant, and then as sort of part of this difference, we use the t-table instead of z-table. Instead of, I guess, normal table. Okay, so that's basically it. As far as like the basic rough outline, this is when we use the t-test. This is what makes it different in our calculations. Everything else is basically the same, okay? So I'm sorry to go a little bit over. I'll do an example of this first thing on Thursday, and then I'll get into chapter 27. Okay? Bye.